First section here is just working with radicals. So like I said, it's just going to be reviewing a couple of things with the radicals. When you're working with a radical, just like when you're working with division, you have the quotient and the dividend and things like that. With radicals, they're different parts of it have different names. So the value in front, oh, yes. Okay, so now we're realigned. So the number in front, just like when you're working with variables, is the coefficient. The number in the notch is called the index. So that's whether you have a cube root, a square root, a fourth root, that's the index. This is just our radical sign. It's just that root sign that we use. And then the number inside the radical sign is called the radicand. So now if we're going to simplify this, basically what we do is we look at, forget about the coefficient in front and think of the cube root of 8. So the cube root of 8 is 2, because you think of what three numbers can you multiply together? What three same numbers can you multiply together to get 2? Which one? Radicand? So your answer there would be a 2. D, radicand. So you'd have 5 times 2, so the solution to this 5 cube root of 8 would be 10. So you have to do your following order of operations. You do brackets first and then exponents. This is still an exponent. It's written in radical form, but it could be written like this. Yeah. So you have to do the radical part, the cube root, square root, or whatever it is, and then do the multiplication or division if it was being divided by 5. Okay, when you're changing a whole number to a mixed radical, and in the last unit, they did that in the answers because they assumed you remembered how when you did that in Foundations 10. But what you're doing when you're changing a number from being a whole radical to a mixed radical is you're checking to see what is the biggest perfect square, or in some cases it could be a perfect, like in B, a perfect fourth root that you could take out. So if you look at square root of 52, square root of 52 is the same as 4 times 13. So you always look what's the biggest perfect square or third root or whatever, depends what the index is, that you can pull out of there. So square root of 4 is a 2, which leaves me with square root of 13. So now I've gone from a whole radical to a mixed radical. Yeah. Yeah. So in B, we have fourth root of m to the 7th. So since my index in this one is a 4, then what I'm looking for is how many sets of 4 can I take out of that. So if I rewrite this, this is the same as saying m to the 4 times m cubed. So if this, yeah, there should be a fourth root right here. So when you're doing this, it's always you're seeing how many of the indexes, how many sets of the index are in there. So if this had been m to the 15, let's say, then I could have had 2 sets of m to the 4. I could have had m to the 4 times m to the 4 times m cubed, and that would give me my, well, that would give me my 11, not 15. So if it had been m to the 11, okay? So you see how many sets of the index you can take out. So if I'm doing the fourth root of m to the 4, that's just 1m that I'm taking out. And I'm left with m cubed. So what you want to be left with is yeah, that's a 4. What you want to be left with is a smaller number inside the radical. That needs to be smaller than your index. Which 4? Right. Okay, C, square root of 63 n to the 7 p to the 4. So square root of 63, well, 63 is not a perfect square, but there is a perfect square factor in it. Right, 9 times 7 will give me 63. N to the 7 can break up into be n to the 6 times n, which would be n to the 7. And then p to the 4, because I can divide by my index evenly, right? My index for this one is a 2. What? When you're square rooting, though, you're dividing your exponent by 2. Okay? So 6 divided by 2 works evenly. 4 divided by 2 works evenly. If you think of it this way, I'm taking my power and I'm dividing it by my index. So it goes in there 3 times evenly and it leaves me with 1, right? This is the same as 3.5. So 3 times 2 gives me my 6 and I'm left with 1. Because I could, if I write it as n squared, then I'd be left with n to the power of 4, right? And another n. So now what I'm doing is I'm doing square root of n to the power of 6. Okay? So first let me do the numbers. Square root of 9 is a 3, so I've taken care of the 9. I can't do anything with the 7 because 7 doesn't have a perfect square, so that one's going to stay. Then I go to my next value, so that's n to the power of 6. So the square root of n to the power of 6, that's the same as saying n to the 6 divided by 2, which is 3. So that means I have an n cubed out here. This n, I can't square root just an n, so it stays. P to the power of 4, square root of p to the power of 4 is same as saying p to the 4 divided by 2. So that means I have p squared. So what I'm left with inside here will be a 7n. Okay. So to go from a to go from a mixed radical to an entire radical, you're doing the opposite. You're going to take a look at what is my index here, and whatever that is, you're going to put it to the power of the number in front. So this one has an index of 2. So that means in order to put it back in, I'm going to have to do a 4 squared. Because if there's nothing there, then you assume it's a 2. So that would be 4 squared times 3. So 16 times 3 is 48. So B, we have x cubed times the square root of x. So my index is a 2. So that means to move it back in, I have to put it back in here, I'm going to have to square it. So this becomes x cubed squared, so times 2, and then times an x. So I have x to the 6 times x, so square root of x to the 7. Well, you add your exponents. Okay. So in this one, my index here is a 3. So that means in order to put this 2k squared in there, I'm going to have to cube this one, and I'm going to have to cube this one. So I have 2 cubed times x squared cubed, and then my 4k was already in there, so nothing changes with that. So 2 cubed is 8. K to the power of 2 times 3 is k to the 6th, and then times 4k. So we have cube root of 32 k to the 7. Because 2 cubed is 8. No, the 4 was already in there, so we don't have to do anything to it. Okay, warm-up number 3 says, write another way, then evaluate. So anytime you have a power that's a fraction, that means it's going to be a root. You're going to have it under the radical sign. This value here is what goes in the notch. So this becomes square root of 16, which when you evaluate is 4. And when you do square roots, you don't have to put the index value of 2. We always assume that just a square root sign is, or just a root sign with no index is a square root. So B, we have 16 to the power of 1/3. So again, that 3 becomes our index. So this is going to be the cube root of 16, which doesn't work out evenly. We can't multiply 3 numbers together to get 16, 3 of the same number to get 16. So we see if we can break it up. So biggest cube root that goes into 16 would be 8 times 2. Cube root of 8 is 2 times 2 times 2. So that means I pull out a 2, and I'm left with a 2. Yeah. So if a question says to simplify and you left this as cube root of 16, you get partial marks because this is the simplified form. Maybe. When you have powers that are fractions and it's not, your numerator isn't a 1, then what you think of is this is the same as saying 8 squared times 1/3. And then you can evaluate it that way. So this becomes this 1/3, there's my index. That goes in the notch. So I have cube root of 8 squared. 8 squared is 64. And as this one turns out, if you multiply 4 times 4 times 4 together, you get 64. So this answer is 4. Okay, when a question asks you to order from least to greatest or greatest to least, what you want to do is you want to simplify them, and then when you write your answer, you should write them so that they are written exactly like this. Okay, so first do your simplifying, and then write them back in the order they appear. So what we want to do with this one, first you take and see, can you change these so that they all have the same value under the radical sign? And it doesn't work. So then what you need to do is you need to switch them back so that they're all radicals. So we're going from mixed radical to entire radical. So 5. 5 is, if I want to put that in as a radical, what value will give me a 5 under a radical sign? Right, square root of 25. So I want to move it back into a radical, and since these are all square roots, then we know to go back into it, to get 5 into a radical, we'd have to square it. So 5 is the same as square root of 25. 3 square root 3. In order to put that back into an entire radical, we have to, since it's a square root, that means we have to square our 3. So that's 3 squared times 3. So that's 9 times 3, so this is square root of 27. Two square root 6. So to put the 2 back inside means we'd have to square it, so we'd have 2 squared times 6. So 4 times 6 is 24. And then the last one is under radical sign already. So to go from least to greatest, the least one then, since these are all square roots, then we just look at the values inside them. So square root of 23 is the smallest. Next one would be the square root 24, which is 2 square root 6. Then is 25, so that's a 5. And then 27 was our next value, so that's 3 square root 3. So that would be your solution to that. Okay, so that was kind of, excuse me, the review stuff. Now we're going in a little bit further, and I think you did a little bit with adding and subtracting, I can't remember, in grade 10. So like radicals are radicals with the same index and the same radicand. So what that means is the number in the notch and the number inside have to be the same. It doesn't matter what the coefficient is, just what the number in the notch and the number in the inside it is. So 3 square root 2 plus 2 square root 2. This is the same if you decompose this, or if you broke it down. 3 square root 2 is the same as saying square root 2 plus square root 2 plus square root 2. 2 square root 2 then is the same as saying square root 2 plus square root 2. This is 3 square root 2. This is 2 square root 2. So if you break it down. So if you count up all your square root 2's there, how many do you have? 5. Yep. So, right. So if the number inside here is the same, so if they are like radicals with the same index and the same radicand, then it's just like they're a variable. This is the same as adding 3x plus 2x. So all you do is add up the numbers in front. You add up the coefficients. So your steps, so you check to see if they are like radicals. So do they have the same index and the same radicand? If they aren't, you just simplify as much as you can. Which means if this one had also thrown in the example up here, 3 square root 2 plus 2 square root 2 plus 2 square root 3, then you would just collect these two, the 3 square root 2 and the 2 square root 2, and then the 2 square root 3 would just tag along. So if they are the same, then you add or subtract the coefficients depending on what was in the question. And you don't do anything with the radicals. If they can't be simplified, or if they're in simplest form already, then you just leave the radicals alone. So what some people end up doing is they say 3 square root 2 plus 2 square root 2 is 5 square root 4, which is wrong. Because 3 plus x, or 3 times x plus 2 times x isn't 5x squared, it's 5x. So the next part says verify that the two expressions above are equal. So what we want to do is we want to see, does our left side equal our right side? So on your calculators, the square root of 2 is 1.4142. That's rounded. And then it'd be plus 2 times 1.4142. Oops. So 3 times 1.4142 is 4.2426. And 2 times 1.4142 is 2.8284, which is 7.071, rounded. So on your right side then, 5 times square root of 2, so that'd be 5 times 1.4142. You multiply that together and you get 7.071. So our left side equals our right side, so we know we're right. So simplifying. These ones, the first examples are nice and easy because they all have the same radical. So 7 square root 3 minus 2 square root 3, you just look at the coefficients in front and add or subtract. So this is 5 square root 3. B, take a look at your radical. It's a cube root of 10 and a cube root of 10, so those are like radicals. So we just add or subtract the values we're given. So I have negative 5 minus 6, so that's negative 11 cube root of 10. C, I have 4 square root 2 minus 5 cube root of 2. These have the same radicand, but they don't have the same index, so they're not like radicals. So that is the answer. You can't do anything else with it unless you changed it to decimal form, and then it's not an exact value anymore, so you don't. Well, you wouldn't even have to write this. I just wrote that as my explanation. Yep. Or you could just write this again. You could say 4 square root 2 minus 5 cube root 2. It's done. Okay, D part. 2 square root 75 plus 3 square root 3. Well, you can tell right away that square root of 75 and square root 3 are not like radicals. But what you need to do is you need to see if you can change them. If you make that square root 75 into a mixed radical, will they be the same then? Possibly. So again, it's always the same step. You see what is the biggest perfect, in this case because it's an index of 2, so what's the biggest perfect square that can divide into 75? 25. So 25 times 3 plus 3 square root 3, that is in simplest form. There's nothing else you can do. And a good hint when you're doing these questions to see what you can, if you can reduce it, is look to see what is the smallest radicand that's there. So this had a cube root of 3. So chances are, if I took that 3 and divided it into 75, it's going to leave me with the other part that I'm looking for. So now I do, what is the square root of 25? 5. So I took care of this one by saying 2 times 5. And this is where people make mistakes. They take this, they do square root of 25, and they don't, or they either drop off or they don't pay attention to that value that's in front of her. That coefficient in front of there is being multiplied to the radical, so it's multiplied to whatever you pull out. So I have 2 times 5 is 10, plus my 3, so I have 13 square root 3. Okay, next one, I have negative square root 27 plus 3 square root 5 minus square root 80 minus 2 square root 12. Nothing in there is the same, but can I change my entire radicals into mixed radicals and get some like radicals? So 27, what perfect square can multiply into 27 evenly? 9. So that leaves me with 9 times 3. Square root of 5 can't be reduced anymore, so it stays 3 square root 5. 80. What perfect square multiplies into 80? That's not a perfect square. 16. Because 16 times 5 is 80. And you always want to look for the biggest one, because you could have said 4. 4 does go into there, but that leaves you with 4 times 20. But 20 has a perfect square in it. 4. 4 times 5. So you always look for the biggest one that goes in there. So this is 16 times 5. Minus 2 times 12. Biggest perfect square in 12? 4. Yeah. So 4 times 3. But when I take it out, then it's gone. My 16 is taken care of. So first thing I do is I get rid of my perfect squares in here. So square root of 9 is going to leave me with a 3. And I can't do anything with square root of 3, so it stays. So I can take care of my square root of 16, which is a 4, and I'm left with square root of 5 in there. And then the last one, square root of 4 is a 2, So I have minus 2 times my 2 square root 3. So negative square root, or negative 3 square root 3. The other like radical is over here, right? It's this square root 3. So that's going to be minus 4 square root 3. And I'm going to group them together so that I have them together, but you don't have to. And then I have plus 3 square root 5 minus 4 square root 5. So I have negative 7 square root 3. 3 minus 4 is negative 1, so that's just a negative square root 5. You could write the 1 in front of there if you wanted to by adding my coefficients. This one and this one have the same, they're like radicals because they're square root of 3. So negative 3 minus 4 is negative 7. And then 3 minus 4 is a negative 1. Okay, the last one there, F says square root of 9b minus 3 times square root 16b. But it has a stipulation on here. B is greater than or equal to 0. For right now, we're not going to worry about that b greater than or equal to 0. We're just going to solve. So square root of 9b, square root of 9, that's a perfect square. That's going to leave me with a 3. I can't do anything with that b, so it stays square root b. Square root of 16, that's perfect square, that's a 4. So when I take care of that 16, I have to multiply it to my coefficient there. So this is 3 square root b minus 12 square root b. So my answer is negative 9 square root b. So all I did was go 3 minus 12 to get negative 9, and I keep my, what's that called? My radical. So underneath it says, in example F, why does b have to be greater than or equal to 0? Yes. Right. Until you do imaginary numbers, you can't square root a negative. So if b was equal to negative 4, you can't have a negative value underneath there. So in the first one, you'd have square root of negative 36, which you can't do. So that leads us, this b greater than or equal to 0 leads us into our restrictions. So it says if the index is even, so a square root, a fourth root, a sixth root, or whatever, so an even value, the radicand must be non-negative. You can do the cube root of a negative number because you can multiply 3 numbers together and get a negative value. So negative 3 times negative 3 times negative 3 is negative 27. So I can cube root negative 27. I can't square root negative 27. So if it is, then the radical is undefined. So like in the other one, if that b value had been negative, our answer, our solution would be undefined because we would have had a negative square root. Cube root would be okay. So it says find the restrictions. Oh, to find a restriction, set the radicand greater than or equal to 0 and then solve. So it's nothing different than we did in when we're finding our intercepts or our solutions in last unit, except we're going to use a greater than equal to sign instead of an equal sign. So to find the restriction of A, I take the radicand, so in this case it's 3 minus m, put it greater than equal to 0, and then solve for m. So in this case, all I'll do is I will add my m to both sides. So I have 3 is greater than equal to m, or if you flip that around, you'll have m is less than or equal to 3. So it's pointing at the m. So that is your restriction. So m has to be less than or equal to 3. So it can be a 2, because then I'd have 3 minus 2 is 1. It could be a negative. I could have negative 7, because 3 minus negative 7 would be plus 7, right? 3 plus 7 is 10. So B, 2x plus 5 is my radicand. I put it greater than equal to 0, and then just solve. So I'll subtract 5, and then I divide by 2. So my restriction is x is greater than equal to negative 5 over 2. So anything bigger than basically negative 2.5 will work. So the last one, I have cube root of x plus 2. For this one, my index is odd. It's a 3. If it's an odd index, there aren't any restrictions. So therefore, there is no restrictions. Because you can cube root, or you can fifth root a negative number. So odd index radicals have no restrictions because, like I said before, you can go negative 2 times negative 2 times negative 2 to get negative 8, which means I can cube root a negative 8 to get an answer of negative 2. So they have no restrictions because you can multiply an odd number you can multiply an odd number of negative values together and you'll get a negative answer. So an example to show you this is cube root of 8. Cube root of 8, that's the same as saying 2 times 2 times 2. So the cube root of 2 times 2 times 2 is just 2. So that means the cube root of negative 8 is going to be a negative 2. Because negative 2 times negative 2 times negative 2 equals negative 8. So that's why it works for odd indexes. So No, because negative 2 times negative 2 is positive 4. That's not a negative 8. Oh. So the last part is just basically an application. How can you use radicals? And how can you solve different problems with radicals? So in this one, it's just a triangle. They've given us a triangle. They've put a height on there. This should go to the bottom. At a perpendicular. So the question says, what is the exact length of AB? So from our stuff in Unit 2, we know in this triangle here, triangle A, and we'll call this where that right angle meets, is point D. We have 90 degrees and 45 degrees, so we know that this angle here is a 45. So triangle ADC, or ACD, whatever you want to call it, it's a 45, 45, 90 triangle. You don't have enough information. Oh, coastlaw. Yeah, I think you could. Yeah, I'm just checking with coastlaw if you have. And then you could, yeah. We're going to use the 45. You could use coastlaw. We're going to use the 45, 45, 90. So we know from our 45, 45, 90 that your sides are 1, 1, and square root 2. So we're going to use trig functions. We're not going to use coastlaw. So what I have here for this triangle ADC, I know this is square root of 12, and I know that this is 45. What I want to find is this little length here, this little AD length. Because we're going to put the two together. Because I want you to know how to do it this way, because sometimes you won't be able to use the coastlaw. So you need to know how to use this. So cosine of 45 degrees, cosine is adjacent over hypotenuse. So that's x over 12. Sorry, square root 12, not 12. From our 45, 45, 90 degree, we know that cos of 45, if we do adjacent over hypotenuse, is going to be 1 over square root 2. So if I have cos of 45 is equal to 1 over, or x over square root 12, and cos of 45 is equal to 1 over square root 2, that means those two equal each other. X over, that should be a 12. I put it all together. So Nicholas, what can I do when I have an equal sign in fractions? Cross multiply. So I have square root 2, x times square root 2 is equal to 1 times square root of 12, so that's just square root of 12. I need my x by itself, so I square root 2, square root 2. So x is equal to square root 6. So I know that this part right here is square root 6. So in my second triangle, or the second half of this triangle, I have a 90, a 30, so that means this has to be 60 degrees. So from chapter 2, oops, pretend that works. We'll finish. Square root of 30, the side opposite that is 1. Side opposite the 60 is square root 3, and the hypotenuse is 2. The triangle BCD. Yeah, this side is square root 6. Where? This one? Or this one? Yes. Yeah, that would be a square root 6 here also. Yeah. Okay, so if we're looking at triangle BCD, what we're trying to find is this length here. So again, we can use cosine. So if we call this little side here y, that's what we're looking for. If we use cos of 60, sorry, not 60, we're going to use 30. Adjacent and hypotenuse. So if I use cos of 30, adjacent is y over 2 square root 2. From my 30, 60, 90 triangle, I know that the cos of 30 is equal to square root 3 over 2. So I do the same thing. I put them equal to each other. So y over 2 square root 2 is equal to square root 3. I'm just going to finish cross multiplying and answering. It'll take about 15 seconds. So 2y is equal to 2 square root 2 times square root 3. So that's equal to 2 square root 6. Because you multiply these two together. Square root 2 times square root 3. And then divide by 2. So y is equal to square root 6. So all together then, if this is a square root 6, AB is equal to, 2 square root 6. Questions? That's okay.